This video on the physics of fluids talks about energy partitioned into energy of momentum, pressure, and a little bit on gravity. Total energy in a fluid can be partitioned into the energy due to pressure, the energy due to momentum, fluid moving in the same direction, and the energy due to gravity, going up or down. In sketches, the energy due to pressure can be thought of as the energy from molecules hitting the boundaries of a vessel. The energy due to momentum is due to molecules that are moving all in the same direction. And the energy due to gravity can be decreased as a molecule goes up and all its energy gets converted to energy of gravity, or increased as a molecule goes down faster and faster due to acceleration due to gravity. All three of these are just movement of molecules. They aren't actually different, except that we want to separate them out because energy of pressure is the force being exerted on the wall of a sphere or a tube. The energy of momentum is what is moving molecules from one location to another, like blood in your blood vessels. And the energy of gravity is the movement that moves molecules up against gravity or down. When we talk about converting these to each other, we're just talking about different directions of motion. If fluid is under pressure in a sphere, then the E total is equal to energy of pressure. There's no movement from one location to another for energy of momentum, and the sphere is not moving up or down, so there's no change in energy due to gravity. If all the molecules are moving in the same direction, then the E total is equal to energy of momentum. Now that's not possible. There would be at least a little sideways movement, but in principle, E total could equal energy of momentum. And if molecules were only moving up and down, then we'd just have changes in energy of gravity. How is energy of pressure converted to energy of momentum? Let's think about our sphere again with molecules moving at random within. That's energy of pressure. Now let's put a hole in the side and a little tube. Let's zoom in on these molecules here. A is moving away, it can't enter the tube. B is moving laterally, it can't enter the tube. C is moving in exactly the right direction to enter the tube. In fact, any molecule that enters the tube has to be moving in this direction. That's energy of momentum. That's a current flowing from one area to another, energy of momentum. Let me repeat. The only molecules that can enter that tube have to be moving in that direction. That means the energy of pressure is going to be converted to energy of momentum. The molecules remaining have lost some energy. Some of that energy is lost to the flow through the tube. They will continue random molecular motion, but it will always be the case that a molecule can only enter this tube if it happens to be going in that direction, energy of momentum. What about the back conversion of energy of momentum to energy of pressure? Let's take our same sphere, but now there's a vacuum in it. We'll have water coming in with energy of momentum. It's coming through this tube, so it has a high energy of momentum. It'll cross the tube, hit that back wall, and all those molecules have to bounce off. They'll bounce off each other, and each new one coming in has to change direction. It has to switch from energy of momentum in this direction to random molecular motion. Eventually, our sphere will be filled. No more water will be able to come in because water is not very compressible. We'll have all that energy of momentum converted to energy of pressure. What happens at a transition zone? Here's a transition between a wider tube going to a narrower tube. We have energy of momentum from the flow coming in. At the transition zone, some of those molecules hit the boundaries of the tube and bounce off. That changes their direction. It converts energy of momentum to energy of pressure. Can that higher energy of pressure be converted back into energy of momentum? It can. That higher pressure means molecules are moving in any direction. Here's A moving away, which can't enter the tube, B moving laterally, which can't enter the tube, and C moving in that direction, which can enter the tube. So we have energy of momentum converted to energy of pressure, some of it, and back into energy of momentum because the only molecules that can enter that tube are the ones going in this direction. What about the opposite conversion from a narrower tube to a wider? Now I've drawn these as if there's only energy of momentum, but of course there's pressure in the vessel. Some of the molecules are going sideways. That's important when you think about this particular transition. Fluid is entering, but these molecules are getting more collisions from the middle of the vessel than from the outside. And so what happens is you get vortices forming in which fluid spins off. Those vortices are changing the direction of flow of the water molecules. This isn't one individual path, but it's individual water molecules hitting each other. Those vortices are collisions of molecules, changing direction. That converts energy of momentum to increased energy of pressure at this transition. Once we move past the transition, the vortices gradually decline, and a higher proportion of the energy is energy of momentum. I've talked about this without considering the effects of resistance, loss of energy to the walls of the vessel. That's going to be the subject of another video.